Hey y'all, welcome back to our discussion on the mind and machine. We are going to talk about how neurons can learn. We're talking about what neurons can do and what neurons can know in the context of computational algorithms, if you will. So now we want to talk about how a neuron can learn. Okay, so we talked about the McCulloch-Pitts neuron or neural model and how we can use algorithms to execute or at least to model biological processes that are happening with neurons. So when we talk about neural learning, the first guy that needs to come to mind is Mr. Hebb, Donald Hebb. Okay, and he talked about the organization of behavior. He published a piece called The Organization of Behavior. In it, he says, when axon A is near enough to cell B and repeatedly or persistently takes part in firing it, some growth process or metabolic change takes place in one or both cells, such that A's efficiency as one of the cells that fires B is increased. Okay? This is a very long way of saying essentially that neurons that fire together wire together. You will hear this saying in reference to Hebb a lot. And it essentially means that the more you use something, the better you're going to be at using it. So the more two neurons connect, the less effort they will need to make to connect in the future. Okay? So if we check out this analogy, sort of the hillside analogy, on one side of the hill you've got a few little tributaries, a couple little streams kind of going on here, but they don't really change much. They don't expand. They don't travel down the length of the hill because they're just working with the water that they have, right? They get minimal rain, and so they pretty much no change here. Now this side of the hill or the mountain gets a whole ton of rain. Okay, it's always getting rainfall. So what happens is that these little tributary guys, they start to widen, they start to get stronger, they start to take off different pathways, root out different pathways of their own. And this is basically what's happening when we have neural networks that fire a lot. Okay, so when you have a network that's constantly being used, eventually what happens is you don't even have to use that much of the network in order to do the same task anymore. So the area required for executing a particular task or cognitive process becomes minimal when you get really, really good at that process. So when we apply what we're talking about, or what Dr. Hebb was talking about with the firing together and the wiring together, we can say that really learning, when you implement it in this model, would be a modification of our synaptic efficacy. And remember that synaptic efficacy had to do with the weights. So the weights, the weighting of the input coming from each of these dendrites is important as far as efficacy is concerned. And when you change that weighting, this is what happens when you learn. Okay, the change of weightings is essentially the algorithmic learning process. Rosenblatt took this idea of algorithmic learning and implemented it in what he called a perceptron. Now, perceptron is a model of a single neuron. It's usually a binary model. So what it does is it takes input and it categorizes it and gives you the output categorization. And that categorization is usually binary when you're talking about a perceptron. So you would have input from retinal units. Okay, this is sort of a visualization of the model. And those retinal units feed into output sort of pattern detector units. And these don't have to be retinal units. These can be whatever input units, whatever cells you're talking about. So here are your output units, right? So we have output unit A, let's say output A, oops, and output B. Okay, so these retinal input units are equivalent to, remember, our dendrites, the X1 through XN number of dendrites feeding into our cell body. Right, so this is X1 through XN retinal input units, and they have to feed into both of these potential. Whoop, hey, Olay. they have to feed into both of these potential output units. So as they feed into these units, the input is weighted, right? We talked about our cell body is summing the weighted input over time, and this is how it is calculating its current membrane potentials. Okay. So we set all of our weights to a random value. Why is it random? You kind of have to start somewhere. You don't necessarily want to start at 0, so you just set everything to a random value. And you give the model a set of input patterns to classify. So let's say we say that if we have this, this, and this, then that should be A. Okay? And if we have this, this, and this, then we want it to give us B. Okay? So we've given it a set of goals, a categorization that we want it, a kind of output that we want it to give us. Now, let's talk about, let me do a little bit of a demo here, and this is going to be kind of a real-time demo, and there's a website with an actual perceptron model, a functioning perceptron model, and we will use that to see a visual implementation of this concept. That's a little bit better than my homemade network. Let's imagine that we have a simple binary perceptron, okay, just like what we were just dealing with. Okay, the input is going to be location. We're going to give it XY coordinates, and the output needs to be color. So we give it XY coordinates or location. If the XY coordinates indicate that the dot is here, the network needs to tell us, the perceptron needs to tell us that it's blue. If the XY coordinates indicate that the dot is here, we need to get an answer of red. So we have two outputs, red or blue. The outputs will be defined by a threshold. Okay, so if you pass a particular threshold, it's red. If you don't, it's blue, or vice versa. And let's look at a little bit of a real-time demo. Okay, this is a simple, as it says, binary perceptron demo. So what we're going to do is we're going to give this perceptron some information. We're going to tell it that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blue dots here, and we'll just give it sort of the same amount over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots here. And then what we do is we just keep training this model. Okay, so you train it, train it, train it, train it, train it, train it. And basically what it's doing every time you train it, it's adjusting its weights. And it's adjusting the weights so that it can properly classify the input that you're giving it. So when we classify all of these dots, okay, it's telling us here, yes, this is all blue and this is all red. So we did a pretty good job. Now, what happens if we start doing something like this? Okay, so now we have some blue dots in there. We have some red dots over here. Let's train it up. Now the network is a little bit more confused at this information, right? So these additional 6 data points change things up. Let's see if we can classify. We're not doing such a great job at classifying this time. So it does matter the input that you give it, right? So if you give it completely, if I were to say, I want all of my blue dots to be here and here, right? So I'm going to give it blue dots here and here, and I'm going to put red dots here and here. Now, this network is going to have an issue with this, right? Because now we don't have, this isn't just a binary output situation. So what you have is if XY is here or here, then blue. If XY is here or here, then red. So that is going to be a little bit more complicated of an input that this particular network needs to classify. Okay. So how is it doing it, right? We are giving it XY coordinates. Here are the weights. Okay, so these weights 1 and 2, they're set to random. The input patterns are the XY coordinates of the dot. And then here is your threshold. And this threshold is essentially saying that if the threshold is 0.5. If the output is below the threshold, the dot's going to be red. If the output is equal to or above the threshold, the dot is going to be blue. So there you have it. You start by setting weights to your random value. You give the model your input patterns to classify. You give it a set of goals, a threshold, right, to which it gives you output. So round 1, we have our first set of input. The first input pattern goes in. The model computes the output. The output is going to be the sum of all of the individually weighted inputs over time. Here, it's not really over time, given that this is our first input pattern, right? We don't have a time factor here. Now, what the network does is it compares the output to your predefined threshold, and it classifies. If the classification is wrong, you start over. You rinse and repeat, round 1. Okay, so you're gonna redo your weights. You're gonna keep going until your classifier gets it right. So that is the basic concept of a perceptron. Now, I have included on Blackboard a video. It's a portion of a lecture done by Dr. Alice O'Toole. And she's in the Department of Behavior and Brain Sciences. They're at UT Dallas, or here at UT Dallas, even though I'm in Houston and UT Dallas is there. Didn't quite know which descriptor to use. She is pretty amazing when it comes to neural networks and algorithms and using algorithmic processes to represent cognitive processes. And so I have sort of pilfered a small section of one of her lectures for you to watch, and it's basically an example of a more homemade, more thoroughly explained example of how a perceptron might work. It's pretty interesting. Check it out. As things do, the perceptron, of course, has developed. So Anderson in the 1980s came up with all of this, which is wow. So this particular network. This is where we introduce feedback, right? So now the network it gives itself feedback. It can say, "Hey, here is my output. I'm going to feed this output back down through the model and adjust my weights accordingly." Okay, so that is one sort of particular kind of recurrent feedback that networks can use. And then into modern day deep convolutional neural networks with multiple convolutional layers, multiple weightings. Your input is no longer just like X and Y coordinates. Right now you have an image, and your image is it's 256 by 256, and each one of those pixels contains information. Right, so all of that information is fed into this network, and the network tells you that, hey, yes, I'm looking at a face, right? So it gets really complicated, and Dr. O'Toole is really good with explaining some of that stuff. So go ahead and watch her model, and that pretty much will sum up how neurons learn. So just to sort of sum up and put all this stuff together, what can a neuron do? It can take in information, it can calculate information, and it can give you an output, right? And we can represent this algorithmically. What can a neuron know? It can know based on the information that it's taking in, and the information that it's taking in is coming from surrounding neurons, right? So it knows in the context of all of its neighboring neurons. And how can a neuron learn? It learns based on the connections that it forges with these neurons and how strong those connections, its neighboring neurons, and how strong those connections are, right? The stronger the connections get, the better the connections are, right? The more used a particular neural network is, a biological neural network, the more condensed it becomes, right? The more expert it becomes at doing its particular task. So this is how we combine all of what we just talked about in the previous videos. I will see you in our next series of lectures, which I believe is sensation, maybe it's hemispheres. I never seem to know what the next series of lectures is, but regardless, I will see you guys there.